Project 5.1 Magnetostatic Levitation Device. This project explores 4 stages of mechanical engineering design processes, including engineering drafting, instrumentation, machining, and software, and also explores physics of magnetostatics and electromagnetism. The purpose of engineering drafts or drawings is to be able to quickly put ideas to paper and have a concept that's in a visual form. While drafting on its own might sound very casual, there are actually several standards and conventions for engineering drawings. Professional engineering drawings generally come in 3 kinds of forms. The forms shown here are 3-view orthographic and isometric. This is an example of a Part 3-view orthographic drawing. This is one of the pieces of the maglev device, and it supports the PCB. The orthographic drawing consists of a front, right, and top view. It also contains dimensions that describe the full shape of the part, including characteristics of each dimension as to whether it's a diameter, a radius, or a linear dimension. The solid lines indicate part edges or tangents, and the narrower lines, such as the crosses through the circles, indicate center lines or holes. This is an example of an isometric drawing, and it contains the parts of the chassis and the upright piece of the maglev device. The isometric drawing is drawn in somewhat of a perspective form, except lines that are parallel on the horizontal plane are parallel as shown in the drawing, and not drawn in perspective or off angle. In isometric drawings, it's common to see geometric features compressed to fill the plane space. For example, some of the circles appear as ellipses, or some of the radii appear stretched or compressed in order to match isometric projection standards. This is an example of an assembly drawing. It contains several parts that connect together to form a larger part, and also contains, generally, a bill of materials. Professional engineering drawings also contain a title block with necessary information to identify the part, such as the material, the weight, the title of the drawing, the identification number, the type of projection, the owner or patenting information, the scale ratio, and initials for who drew the drawing and who verified it. While engineering drawings often start as handwritten, they can be translated into CAD files. These CAD files can be uploaded to CNC machines to produce solid replications of the drawn parts. Some parts, like this coil mount here, are machined using manual machines, such as lathes, drills, and mills. The coil mount was turned on a lathe, such as the one shown here. The lathe turns the part at a very high RPM against a cutting tool like carbide. The result is a fully rounded feature about a central axis. Another commonly used metalworking machine is the mill, which was used to cut this aluminum PCB mount. The mill uses a flat-headed drilling tool to scrape material off of a workpiece. All of the machine parts are used to form a case for the magnetic levitation device. Inside the case is a circuit board which controls the magnetic levitation. This is a diagram for the magnetic levitation device circuit. Some noteworthy components in this circuit include the Hall effect sensor shown in the upper left corner and the inductor shown in the middle right. The inductor used in this circuit is hand-wrapped, and instead of being directly attached to the circuit board, it is connected by wires and fastened to the top of the chassis and upright piece. As a circuit component, the inductor resists changes in current by storing magnetic energy. Otherwise, the inductor creates a magnetic field based on the current running through it. The magnetic field created is dictated by the Biot-Savart law, which states that the magnetic field is proportional to 1 over r squared, where r is the distance from a wire with an active current. The levitating piece contains 2 rare earth magnets. The top one interacts with the magnetic field created by the inductor. The bottom one creates a magnetic field that is detected by the Hall effect sensor in the circuit board. This is the top face of the circuit board. The Hall effect sensor is located at the very lower end of it, directly underneath where the levitating piece and the inductor coil are situated. The Hall effect sensor produces a voltage output according to the polarity and intensity of the magnetic field detected. While the inductor is a primary source of an electrically induced magnetic field, permanent magnets are a constant source of magnetic field. The input from the Hall effect sensor and the variable resistors labeled offset and gain help control the magnetic field produced by the inductor and consequently the magnetic force exerted on the levitating piece. This project was part of the University of British Columbia's Mechanical Engineering Technical Practicum course for second years. Thank you for listening.